In this video we're going to talk about equilibria, and this symbol is very important for that. Equilibria are what happens when you have two competing reactions. Now, that's not usually thought of as one reaction, another reaction. We think of it as one whole reaction. We've dealt with one of these before. We've looked at the Haber process. Now, in the Haber process, you've got two reactions. You've got the one that takes nitrogen and hydrogen and gives us ammonia. We need to balance this, of course. We've also got a reaction that goes the other way, taking ammonia and breaking it down into nitrogen and hydrogen. And that's a problem. We want to make ammonia. We don't want to have the reaction going back the other way and making our starting materials again. Now, we could, every time we talked about the Haber process, write down both of these reactions, but that's not very efficient. Chemists are lazy. So what we do is, instead of having that single arrow, we have a double arrow. It's like an equal sign with half an arrowhead at each end. And that tells us that this is a reversible reaction. It will go in both directions. That's really handy to know about, because that lets us manipulate what's going on. Now, I said we were talking about equilibria. And at equilibrium, the equilibrium point is where these two reactions cancel each other out. So we're making ammonia at the same rate as we're breaking it up. It's not that either reaction has stopped, they're still going on. But it's like you've got a bucket of water. Let's have a bucket of water. Here's our bucket with some water in. And over here, we've got one person with their own little bucket, and they're putting the water in. And over here, we've got someone else with their little buckets taking the water out. Now, neither of them stops putting water in or taking it out, but when they're working at the same speed, the bucket is going to keep with the same amount of water. That is an equilibrium case. At some point, this person could be faster. That would disturb the equilibrium. We need to talk about that. So that's the first thing, equilibrium, where the forward and reverse reactions cancel out, where both of these men with the buckets work at the same space. Now, we can change this. These two men, they're in competition. And it works like that for chemical equations as well. They're trying to stay at equilibrium. If we speed this guy up and he starts putting more water in, this guy is going to speed up to take more water out and get back to our equilibrium level. So if we change the conditions, it's going to change how the reaction works. For instance, let's talk about rocket fuel. Let's get rid of the Haber process. Did that before. Let's do rocket fuel. Dinitrogen tetroxide, N2O4. Lots and lots of oxygen in there. Really useful for propellants. The old space shuttles used it. It's a really useful compound, and it's in equilibrium with nitrogen dioxide. Now, we need to push the equilibrium towards this side. Now, just notice I'm going to add a little thing here. I'm going to put a G and a G. That means these are gases. These are state symbols. They tell you at standard conditions how these are. So these are gases, both gases, in standard conditions. Now, if we add more nitrogen dioxide, that's going to unbalance the seesaw of this reaction. Our two little people with their vat of water, that's what's gone on there. And that means this guy has to work harder. What it means for the reaction is, if we add more in here, we're going to push towards this side. So we'll make more of this one. This side gets higher as well to balance it out. If we double the amount here, we'll double the amount there to balance it. Or nitrogen tetroxide, that goes away. It'll pull more across, basically. We take some away, this will react to make more, getting it back to equilibrium, getting it back to being balanced. So that's two things we can see from there. Now, what else? If we increase the pressure, what's going to happen? Well, the way for the reaction to reduce the pressure back to where it was, which is what it's looking for equilibrium again, would be to move this way, because that's going to go from a concentration like that to half as many molecules. 12 over here, 6 over here. This is going to have a lower pressure. Each of these can exert a little bit of gas. We could know some other things about this. For instance, I can tell you that this is exothermic, which means it gives out heat. That means in order to speed this reaction up, we need to cool it down. So the forward reaction that produces more heat is going to heat it up again. It's trying to get back to where it was when it was at equilibrium. So you cool it down, this reaction is going to be favoured. Because this is exothermic, we know that going back is endothermic. So heating it up, the reverse reaction is going to be favoured to cool it down again. It will react to get back into balance. That's good for us in that increasing the forward reaction increases our yield overall by cooling everything down. But for the overall kinetics, the speed of the reaction, this is bad. It's going to slow down the speed with which we get to it. So there's always going to be this trade-off. Remember, in the Haber process, we have those compromise conditions. All of this has a name. It is Le Chatelier's principle. Le Chatelier, of course, early scientist, came up with this. Le Chatelier, French guy. If you're doing research on the net, Le Chatelier's principle is where to look for it. And it states that If a change is made in a closed system, which we assume we are in, the equilibrium will shift in a way to reduce the effect of the change. So like I said, if we cool it down, it will try and heat it up, going that way. If we increase the pressure, it will go this way to reduce the pressure again. If we increase the number of particles on one side, it will react to reduce those, increasing the number on the other side to balance it out again. So we can manipulate those in order to do that.